This is another example truss problem. I call it easy truss 3. What makes it easy, again, is you have a top chord and a bottom chord that are parallel, which you'll see here in a little while. So when we cut it, the sections to analyze it, the only internal member or unknown that has a vertical component is this guy here. And so it just makes the sections a little bit easier. Also, this truss overhangs. It's cantilevered out from a wall, like a sign truss or a crane, something like that. And so to analyze what we need to analyze, we don't need support reactions. And so that makes it kind of easy as well. With this loading hanging down here, this whole truss is going to bend downward. And so the top of this guy and this guy are all going to be in tension, and this bottom chord is going to be in compression. And then these internal guys are basically going to alternate tension and compression. So those are some things that you can think about as you start working this problem. Finally, there's actually a couple zero force members in this truss. So if you analyze the joint at G, that's the T rule. There's no load hanging there. And so if you analyze that joint, this guy is a zero force member. And finally, up here oh, that's not true. That's not true. I labeled this as a zero force member, but it's not zero force, because this is a pin up here, and this pin is going to have a vertical force and a horizontal force. The vertical force here at A is going to be 120 plus 240, which is 360. So there's a vertical force here, it's 360. And so this member, if you analyze the joint at A, so this is A, there's going to be a horizontal force coming to the left. There's a vertical force here, and then of course the truss itself. And then there's going to be a force here at K. So A does have a vertical. And so this is not zero. Okay, so that's incorrectly labeled, that's not zero. Okay, so the problem asks us to find the forces in EF and FG. It also asks us to find the forces in CD, DI, and HI. The problem asking us to find the forces here suggests a joint at F, which we'll do. And finding the forces here suggests cutting it here and then using the method of sections there, which we'll do. So let's analyze the force at F. And so again, what I'm going to do is draw the free body diagram of F. And I'll walk you through that process. So at F, I have a downward directed force, which is 240 pounds. There's a horizontal guy here, which is going to be FGF, FGF. And then I have an upward directed guy that acts along this line of action. And that's a 5, 12, 13 slope. So 5, 12, 13 slope. And that's F, EF. Again, the dotted lines give me the line of action of these forces. And you know, because these are two force members, that the line of actions of these forces are going to be along the members themselves. But I didn't draw the arrows yet because we still have to figure out whether this guy is pulling on this joint, this is joint F, or whether they're pushing on point F. If you do the X direction first, you can't tell anything. But if you take, again, if this is X and this is Y, but in the vertical direction with the load hanging down, it's clear that FEF is going to have to act upward. In other words, it has to be pulling on F to keep this guy in equilibrium in the vertical direction. And so if we draw him pulling, that means I'm assuming that he's tension. And once we figure that out by looking at the Y direction, then if we think about the x direction, there's no x component here. The x component of him is to the left. And so basically our FGF is going to have to act this way. And so he's going to have to push on F, which is basically assuming him in compression. So again, that's how you would intuit the forces at joint F. Once we've drawn the free body diagram, then we can write two equations for this joint in the x and y, usually in the x and y direction. So again, this is a 5, 12, 13 slope. And so if I sum forces in the x direction first, then I've got two unknowns in that equation. So I can do it, but I prefer to get an answer. And so if I sum forces in the vertical direction, then that only involves the 240 and then the vertical component of FEF. So if I take up to be positive, I have 12/13 of FEF minus 240 is equal to 0. So FEF is equal to 260 pounds tension. If I sum forces in the x direction, I've got FFG minus 5/13 FEF. It's 5/13. 5/13 FEF is equal to 0. And so FFG is 100 pounds. And again, it comes out positive, and I assumed it compression, so that means it indeed is compression. So that's the joint at F. To analyze the forces in here, we need to just cut it here, which is the method of sections, and then draw a free body diagram of either the right-hand side or the left-hand side. If I draw the right-hand free body, then I don't need to find support reactions, and I can just use these forces as they are. If I take the left-hand free body, then I have to find the support reactions, which is more work. And so obviously on an exam, you're trying to find the shortest path to the right answers, not the longest path. So let's come down and let's draw this free body diagram. And again, one of the things you can do is just lay a card on top of this guy. And you can actually draw the forces this way. So the top is in tension, bottom is in compression. With these guys acting down, this diagonal is going to act upward. And so you literally could use this as your free body if you chose on an exam without redrawing the whole thing. But I'll show you how to redraw the whole thing. And so what I would do is I would draw this rectangle first for the D, E, F, H guy. And then you have this diagonal down. You have this diagonal down. You have the 240. You have the 120. You have okay, so we already decided that the top chord is in tension, so I'll draw him pulling, and that's F, C, D. We decided that the bottom chord is in compression, so I'll draw him pushing, which is F, H, I. And if you analyze this guy mentally in the vertical direction, with the 240 and 120 pulling down, with neither FCD or FHI has a vertical component, the only unknown with a vertical component is this guy, so he has to be pushing upward. And again, this is a 5, 12, 13 slope, and that's F, DI. And so his vertical component has to equal to the sum of these two, which is 360. And again, this is one of the things that makes this truss easy, is that with parallel top and bottom chords, you just have the one, you can get this FDI with one equation. Finally, we want to dimension it because we're going to be writing moment equations. So this is 5, this is 5, This is 12. And we're going to extend him out to here, which is point I. And this is 5 as well. And we'll write that moment equation as a alternate 2. So that's a free body diagram. Let's write the equations based on that free body diagram. And so in the vertical direction, the only unknown with a vertical component is FDI. And that's at a 5, 12, 13 slope. 5, 12. So in the vertical direction, we've got 12/13 of FDI minus 120 minus 240 is equal to 0. So FDI is 390 pounds. And he comes out positive. We drew him compression because he's pushing on D. And so it's 390 pounds compression. To get FHI, we can sum moments about D. So D is the intersection between two of our unknowns, FCD and FDI. So if we sum moments there, then we have FHI in that moment equation. The 120, his line of action passes through D, so he's not in that moment. But then we have the 240 times 10. So if we sum moments about D, and if we take clockwise to be positive, then we have positive 240 times 10 minus FHI times his moment arm, which is 12. And then FHI is 200 pounds. And we do him pushing, and so he's in compression. Finally, now that we have FDI and FHI, we can sum forces in the x direction to get FCD. That's the easiest way to get it. And so if we take to the right to be positive, we have FHI, which is 200, plus 5/13 of FDI, which is 390, minus FCD. And so FCD is equal to 350 pounds. We drew it in tension, pulling, and so it's in tension. Finally, there's another way we can get FCD. We can actually sum moments about I. And again, I is not on the free body diagram, but that's okay. That's permissible. We can still slide this force along his line of action. We can slide this force along his line of action. They intersect at point I. And so we can sum moments about point I. And about that point, we've got 3 terms. We've got the 120 times 5, the 240 times 15, and then minus the FCD times his moment arm, which is 12. And so if you write those terms, you get FCD is equal to 350 pounds tension, which is the same thing we got from the X summation. So either or, you don't have to do both, either or. And probably the FX is easier, but occasionally a test problem will say, can you write FCD with one equation? And again, if you extend this force, you can get FCD with a moment about I. And you should be able to recognize that.